We're going back to I have to say, Connor might know. He knows the ins more than I do of what occurred after the range club finished.
Okay, we're going to resume today where we left off on Tuesday, going over the last couple of paramaterials that we had. Alluvium. First one we're going to pick up here. Alluvial sediments are really anything deposited by modern rivers. So more sediments from flowing water, pretty similar to our glacial outwash. Sometimes a little landscape knowledge is required. Was this a glaciated area? Did we have glacial meltwaters flowing over this to tell outwash from alluvium? But usually it's not that hard. If you can look around, if you can tell you're in a floodplain environment, if you can see the river nearby, chances are it's alluvium material. Characteristics of it, it's very well sorted, meaning the same kind of size particles are all grouped together. So you'll have all fine sand together from the flowing of the water, or coarser sand, maybe even some gravel involved when the speed of the water was faster. So it's possible to have both fine sand and coarse sand or rock fragments, cobbles in a profile, but there will be some kind of order to them, all deposited in the same kind of horizontal layers rather than completely mixed up the way that glacial till is. Usually found in floodplains or alluvial fans. Alluvial floodplains are probably familiar to everybody, just kind of the low-lying area next to a river that's most likely to flood if the river tops its bank. Historically, really popular, common areas for like development, especially thinking about the origins of civilization, right? Was the Fertile Crescent in the Middle East was two large floodplains that kind of civilization developed in, but also thinking about agriculture, thinking about low-lying flat soils, good availability of water and nutrients, probably fertile soils delivered by floodplain sediments, make them popular for agriculture and settlements in general here, but also alluvial fans are an interesting landform. Most common where we have like mountainous landforms that transition to something more flat. So you have a really high gradient or steeply sloping stream that's probably carrying sediment very quickly that all of a sudden levels out. So it reaches the floor of the valley or the foot slope of the mountain or steep hill. And then the flow rate of the water slows down a lot. The rate of flow slows down, coarse particles fall out of like the suspension. They can't be carried anymore by the slow moving water, or the water itself spreads out across this flat landscape. And you have this kind of cone shape or fan that starts to build up. This is a really, really clear example. Unfortunately, they're a little harder to spot around here. I think I'm still looking for really good examples of alluvial fan landforms, but likely found where you have rivers or streams flowing out of mountains carrying sediment. All of those are together alluvium paramaterials. Next is organics, whereas all the other ones are talking about sand, silt, and clay, sediment delivery. Organics can be its own paramaterial where we have a lot of biomass being produced in place in a soil profile. Where we have this, or having this great buildup means we have plant production outpacing the decomposition of organic material. Where we have our decreased decomposition rate could be any combination of cold or wet areas. I think about like wetlands where we have like these peat bogs, really wet areas. Common place to have a lot of organic material build up, and then we recognize this through our O horizons. So this one on the right is a really organic rich soil, multiple layers of O horizons for up to 1 meter or more deep. I think this is from Bonner's Ferry area of North Idaho. And then the picture on the left was our example of the L master horizon, the limnic at the very bottom, this kind of tan, white, grayish color. That's the special kind of organic material deposited by a aquatic organisms like the diatoms specifically. Above it, though, is more O-horizon organic material from probably the productive wetland vegetation. Anywhere you have a really thick O-horizon, I would say organics are the parent material, just because maybe you have an OI layer at the surface because it's like forest litter, doesn't necessarily make it its own parent material of the soil. Only when this really kind of dominates a profile would we say the parent material is organic. And then our last one is called colluvium. Colluvial sediments are anything deposited primarily by gravity. Gravity deposited sediments usually don't travel too far, is what that means. And I'm just thinking about like just a downhill kind of erosion procedure. So colluvial sediments are also going to be poorly sorted. It can be any texture, kind of similar to our glacial till, but these are probably non-glacial areas or anywhere where you have like a lot of relief involved where sediment can be delivered from or can be received somewhere from somewhere else further uphill. And since these rocks probably haven't traveled very far, they have sharp corners, very angular shapes. They've just kind of broken off from some kind of source rock or bedrock layer and maybe tumbled downhill to reach some kind of resting place towards the bottom, maybe at a footstool position. But this short travel distance for them compared to like a glacial till boulder that's been tossed and turned and rounded off, tumbled across landscapes for miles and miles, those will have generally rounded edges, whereas the sharp and angular edges have not traveled quite as far. And also found at the bottom of slopes. So in these kind of example profiles, this is from a soil judging contest we did in Colorado a couple of years ago. It's really, they're sharp cornered rocks. This was at the bottom of like a really steep slope. That's easy to think of as colluvium parent material. But then also this is a picture from Palouse Falls State Park. This is looking the other way from the waterfall, if you guys are familiar out there. It's a really great example of kind of residuum parent material in a specific landform, in this case, where we have this like really steep gradient of, or steep slope that levels out. Basically, just these are rocks, gravels, cobbles that break off of these cliffs and accumulate at the bottom. So it's such a great example. It's literally the textbook example in the soil survey manual. So we're familiar with like the red spiral bound books of that's the NRCS field book for sampling and describing soils. That's kind of the quick reference version. If you're ever reading in that and you need more detail or it provides a reference for further reading, it will be to this green book, the official soil survey manual, and our Palouse River in Washington, or the Palouse River Falls Canyon is the textbook example of one of these landforms in that book. So I think that's really cool. And then lastly, if we're going to kind of, or what interpretations we can make about parent material if we're going to really if we want to study the effect these have on soil, comparing across different parent materials is a litho sequence. Litho kind of meaning rock, so it makes the most sense when it's like a bedrock comparison. But we would say litho sequence for any kind of parent material change. This picture here is an example litho sequence from my own pedology class in undergrad back in the Midwest, where we have a bunch of glacial landforms to compare. On the left side, we have glacial till parent material. So this was like a clay loam texture with a bunch of gravel mixed in with it all over the place. Then we had glacial outwash, so a little more sandy over shale bedrock. So right here where it gets a lot thicker, chunkier, this is a really clay-rich, really fine, long ribbon kind of texture here. But on the top, it had some glacial outwash, sandier, well-sorted sediments over it. And then this is another outcrop of that shale, clayey bedrock underneath an organic pit. So in like kind of a wetland where we have organics as the parent material over some residuum. So that was a really, just within walking distance, we did these auger holes for a lab one day. I enjoyed that. But I just enjoy parent materials in general because they provide the color, texture, or coarse fragment changes. They really tell the story of any given soil profile. So just some of my absolute favorites are soil profiles with these really beautiful differences in colors, differences in textures that just, they paint a picture, you know, of what happened on the landscape. So I would love to talk more about each one of these pictures and the story that it has for us, but we need to move on to be continued later, maybe bonus geology content in the future. Switching gears to today's topic. Still got the share going, that's good. This is where we start.
I think from the beginning, all I wanted is just more time with you. We've only had on little bits here and there, but I think we've had really good conversations. And I mean, I've opened up to you around, you know, some of my biggest insecurities, and you know, you kind of share your insecurities as well. And it just made me feel really good. I think we want a lot of the same things. We kind of share a really similar perspective on life, and I'm just really excited about you. Just, I was kind of thinking about the other day of, you know, when you kind of have a picture in your head of, okay, this is what I want. You're like, okay, I want to be married, I want to have a family. And then I just kind of started picturing you in that. And it's scary because I can see the possibility of a future with you. I just want to know, like, can you see that possibility with me? Or I guess I'd rather know now instead of, and I know you can't, like, obviously say too much, but
You know, from night one, our first conversation, I was instantly drawn to you. You're vulnerable with me, you're beautiful, and compassionate, understanding everything that I'm looking for. And it was a no-brainer that I could be the first impression artist. And I was so comfortable in our relationship that I explored other relationships. And in exploring those relationships with other women, going on those one-on-ones, I did grow strong feelings for them. And being honest with you and following my heart, and my heart's pulling me in another direction. I apologize. The last thing I want to do is lead you on and lie to you. You deserve someone who's going to put you first.
I mean, I really do appreciate you being honest.
Again, I apologize. Let me call you out. Sorry, I wish I had more time.
Okay, if we keep watching anymore, I'll probably start crying too, but this does really, Logan. Yes. So did you hear the one thing that both of them said? This is from The Bachelor from a few years ago. This is Matt James and Abigail was the Bachelor contestant. One thing that they both said was, "I just wish we had more time." Right? To me, that sounds like they're both entisols that lack the time to develop distinct soil horizons. You know, it takes hundreds of thousands of years sometimes to develop a soil profile, and most entisols just haven't had that amount of time or just aren't in an environment that supports or facilitates good soil development, which is actually not unlike The Bachelor itself, because they film a season in what, 4 or 5 weeks and expect it to end in engagement. There's so many lights and cameras and manufactured drama all the time that probably not surprising that the historical success rates of bachelors and bachelorettes with their final rose person hasn't really worked out. We've talked about the NBA a lot as one of my interests, hobbies, pastimes. We're getting into another one now. It's been a little while since I've tuned into a full Bachelor season, but anybody here a fan? Anybody watch? Anybody keep up with it? Macy does. We just had Jen's season end, right? Not good. It was, I'm still catching up on the drama, but it was Bachelorette season, and the guy she picked that she proposed to was the twist.
I've heard about this, yes.
Yes, but it, like, as soon as the filming stopped, it just, it was like, oh man, tough. So, right, how do entosols have their soil forming environment? How do Bachelor contestants have their relationship developing environment? Plus, the common criticism of The Bachelor these days is that people just go on to get their Instagram followers and launch their influencer career, right? The Bachelor producers kind of knew about that, or at least understood the criticism that these contestants, they're not going out for the right reasons, if you will. They're not ready to get married. So what's the solution to that? What can they do instead? A year ago, the solution was, let's cast a bunch of old people, called the Golden Bachelor. That one also kind of same result. They got married. Gary, right, was the Golden Bachelor. Picked his final rose winner. They got married on TV, right? It was a broadcast ceremony, and then just within a matter of weeks, it was they're filing for divorce. But just was it only this week, the newest Bachelor season that started is a continuation of that one. We're doing from the Golden Bachelor, we now have a Golden Bachelorette. So they got a new cast of senior citizens on The Bachelor. I would love to tune in and keep up with it. I'm not sure how much Golden Bachelorette time I'll have this season. My parents keep me updated though. My mom and my sister enjoy watching, so that's what got me into it in the first place. But yeah, don't worry, Abigail. She's fine now. She went on the next. She returned to the Bachelor franchise, got engaged to somebody else, living in somewhere in the South, I think. Good for them. Anyway, that's enough about The Bachelor. We can actually come back to it later too if we want. But our 5th of 5 soil forming factors, right? Time as a soil forming factor is perhaps our hardest to characterize, our hardest to describe, because why is this? Time itself is like an abstract concept in some ways. It's easy to put a number on to characterize the amount of rainfall we get somewhere. What is the parent material? What is the kind of forest? What's the vegetation community here? What's our microbial population like? What's our hillside position? Those are easy to describe, but time is much harder, because when is time in the context of soil profile equal to 0? When is this T0 point? Is it when does T equals 0 when there's less it's deposited, but what about what was there on the ground surface before it? Is it when is equals 0 when the sediments if we have soil forming from bedrock, is it when it weathers into soil, or is it when the bedrock itself is formed? I mean, we haven't really created any new matter or created any new sediment in the history of Earth, really. So is T equals 0 the same 4.6 billion years for the whole entire age of Earth? It's really hard to describe. So not only is time equal to 0 for the soil itself, but we also have to think about our point in space and time, so our location, considering the soil surface itself could change over time, like are we interested in the ground surface that we see today and any lifting that took place, or when the ground surface maybe used to be higher before some erosional process or used to be lower before some kind of depositional process? How are we varying? What is the ground surface? It's like this whole space and time continuum, if you will, getting into these really abstract concepts, but still we really struggle to define when is time equal to 0. That's what makes this kind of hard to think about sometimes. But usually, truth is probably somewhere in the middle with this t=0 question. We can think our way through it most times based on the most relevant processes or the paramaterial that we have. If we're interested in this soil profile and we can interpret what the paramaterial is, that will usually be most relevant. The length of time for soil development, since the most important paramaterials in the profile have been put there. Just kind of makes this a difficult topic to consider. When we want to consider the effect of time on soil development, we would probably do it through our chronosequence, which is our last comparison word. Chronosequence, right, just like the others, it's a comparison of soil across time, but in this case, our time is in quotation marks because how can we meaningfully compare different times? We had the example in that biosequence in the San Dimas, California, where we had differences in soil formation due to the vegetation, but observable within some kind of like 90-year almost human lifespan. That's great, but like any significant effects that time has on soil development are not going to be visible within a human time frame. Right, we can't meaningfully compare soil across time or some kind of meaningful comparison from the soil's perspective. So for that reason, we often substitute space or like our location for time. A space for time substitution is something that I heard about a lot. I heard talked about a lot before I really understood what it means. But since we can't describe a soil pit and wait 10,000 years to see what happens to it, instead we're going to describe a soil pit in one place and then find another place nearby for one reason or another that we can assume to be 10,000 years older, or go through the same kind of, experience the same amount of soil development, right? To have a space for time substitution. However, the kind of limitations on this, you can't just go anywhere and assume this will work. You need to have the sites be representative of successive stages of soil development. So first this horizon develops, and then this one, and then this one. You have to assume that they all experience the same, or that they represent kind of a progression of soil development, but then they also pass through the same stages over time. Since we can't observe, periodic changes in the soil on the soil's timeline, these are pretty heavy assumptions. That would be one of my top 3 uses of Time Machine, I think personally, to go back 10,000 years, do a soil pit, and return to it 10,000 years later. I would probably want to watch the big Missoula flood outburst if I could from a safe distance. I would love to witness that. But describing time on the soil's timeline, that would be pretty great. However, when we are able to set up these chronosequences to have reasonably safe assumptions of these exact properties. When we can put that together, you can create something that we refer to as a chrono function, which is like an equation or some kind of relationship of a soil's age to some properties that we observe. So what this allows you to do is then take in another soil profile, maybe somewhere else, that has some kind of properties that we can describe as pedologists, and then apply this chrono function and estimate an age of the soil profile, how long it's been developing in order to produce these properties. The thing about chronosequences, right, is that they really restrict us to relative timelines. So first the soil looks like this, and then this, or this profile, because of these characters, are supposed to be older than this other one. So it's really only a relative determination of soil age or measuring time, unless we're able to do some sort of absolute dating. We have multiple different strategies or methods here to determine an actual age or like an absolute date. And a lot of these involve a kind of radioactive decay of specific elements over some kind of known half-life, or a known decay rate of these specific elements that will inform us of the age. So just to review a little bit of chemistry fundamentals here, I'm assuming there's varying levels of experience and interest and excitement upon finishing your last chemistry class to forget all the things we learned maybe. But to review a little bit, we've got our example element here, or any atom, I suppose, contains both protons and neutrons within the nucleus of the center of the atom. The protons, neutrons, and electrons are the three different components. Electrons have essentially a zero mass, they're negligible. So if we're talking about atomic mass of any one of these elements or atoms, it's really the number of protons and neutrons put together. The number of protons in an element determines what element it is, or the number on the periodic table, of course. Put neutrons and protons together, that's the atomic mass. So it's possible to measure the mass of these atoms through lab instruments. Like a mass spectrometer is essentially like a balance or a scale for these individual atoms. And where these differences, or what this kind of whole field relies on, is measuring different isotopes. So an isotope is the same element, so it has the same number of protons, but just a different number of neutrons from what we would expect. So it changes the atomic mass, but not the element itself by changing the number of protons. So for example, if we're thinking about an example isotope, we could take carbon, which we know to be element number 6. Carbon has 6 protons. Usually, the atomic mass from the periodic table we know is about 12. So 6 protons and 6 neutrons is the normal status of a carbon atom. But we have multiple known isotopes of carbon, including 14C, C14. 14 refers to its atomic mass, which means we know we have 6 protons because we're dealing with carbon. So now in order to get to a mass of 14, we need 8 neutrons. So a carbon atom, 6 protons and 8 neutrons would be this 14C isotope. So this is just one example of carbon. We're going to talk about this first. There's many different elements that we can use with different strategies effective over different ranges. So in that case, it means we have many different dating options, which all of a sudden sounds a lot like The Bachelor once again. So here we are with our many dating options, and we can go through these. We're going to go one element at a time. I want to share just a little bit about why this element is used, why it's kind of relevant to this process, and kind of an effective range of it. I do not need you guys writing down and feeling responsible for memorizing exactly the duration of the half-life, how many millions of years this lasts, or needs to do anything too complex with it. I just want you guys to remember that there are different options to do this, and maybe like the relative age range, or like the which ones work over longer times than the others, perhaps. That's about all I'd be looking for. But our first dating option, like we mentioned with carbon, these different isotopes of carbon are introduced usually through photosynthesis, incorporated into organic tissues, organic matter. How this works in the first place is we have an isotope of nitrogen. These cosmic rays and radiation coming from space that will interact with some of these nitrogen molecules and maybe split some of these nuclei apart or substitute protons for neutrons. Essentially, we're creating 14C from 14N that gets incorporated into gaseous CO2 in the atmosphere at some kind of standard rate across the whole entire atmosphere. And then this CO2 that includes this 14C isotope is then going to be taken up by plants, animals, and or humans will come by and eat the plants and incorporate this carbon isotope into the organic material of our own like biomass. So it's still just regular carbon. This has really no effect on our human tissue development in the first place, but still it's incorporated in addition to 12C, our normal carbon isotope, and 13C, according to this constant ratio, the different carbon isotopes. And then, right, 14C is the isotope analyzed in organic materials. And then this 14C will begin to decay because it's less stable in the environment than our normal carbon carbon atom is. So according to our half-life of 14C, which we know to be a little less than 6,000 years, so we can analyze some organic materials, and based on the amount of 14C that we observe in them and its ratio to the 13 and the 12 mass isotopes, we can apply this half-life to predict when the 14C variety stopped, when it started decaying, which would have been when the organism was alive. For example, so the effective range on this is, thanks to a 6,000 year half-life for 14C, that is extended out into the effective range, making it around 50,000 years, which is really relevant for like human history, human timescales. And so in addition to like 14C dating of plant material or tree rings, or organic compounds within soil profiles, relatively recent ones, you also hear about 14C dating within anthropology, archaeology, like if there are human remains such as mummified remains or human beings that were otherwise preserved, the age of them or when this human used to be alive, often determined through 14C dating. But then the same thing with dendrochronology or tree ring research. If you have a really old tree ring or some kind of preserved wood sample, you can use 14C dating to determine just how long ago that tree was performing photosynthesis. So carbon dating is our most recent strategy. If we need to go a little bit further into the past, we might use beryllium as our isotope. This has a similar kind of origin from the upper atmosphere, in this case for beryllium 10 as the isotope. This is another cosmic ray interaction with nitrogen or oxygen in order to produce our smaller element of beryllium, only 4 protons. In this case, it's 4 protons and 6 neutrons. It's occurring with this atmospheric interaction, and then it's falling deposition through like rain and precipitation onto the soil surface. And from there, it just incorporates into the soil profile, and it usually stays kind of right at the soil surface. Beryllium doesn't really move through the profile at all. So it's useful for analyzing soils or sediments, and specifically determining the time since that sediment was exposed to the surface or on the surface exposed to the atmosphere. The beryllium 10 half-life is now 1.4 million years, so it's a lot longer than the 14C. But that gives our effective range of thousands to millions of years. So this is more maybe on a soil time span where the carbon was more on organics or kind of human history and evolutionary time span. This is more of soil profile age. And right, main use is determining time since exposure. So if we have multiple parent materials or like a buried A horizon that could have been thousands to millions of years old, we could do some analysis of the beryllium isotopes that remain in the profile to determine when that, maybe when this landslide occurred or whenever this surface used to be the ground surface, when now it's buried at somewhere in the soil profile. Time since exposure. Continuing on our journey back through time or extending our half-lives here, next is potassium-argon dating. This isotope now it begins as potassium-40, and it's introduced through the mineral structure of some like mineral crystals. And what we have, how this works is the intense heat and pressure environments of magma chambers, or if you can imagine hot molten rock in the form of magma, that can create a potassium isotope where we have these 19 protons to be the element of potassium, and then 21 neutrons, so one extra neutron gives us potassium 40, and then it will crystallize. So as maybe the magma begins to cool, we're forming these primary minerals out of magma. This potassium isotope gets incorporated into a mineral structure. Potassium 40 here has a half-life of about 1.25 billion years, so it's a really long half-life, but still it's going to decay over time. And this decay product is argon gas. So these potassium atoms themselves convert, naturally decay into argon gas that's trapped within this mineral lattice, if you will. So in order to analyze this, you can take this mineral structure sample and either melt it down or denature it in order to release any amount of argon gas contained in the crystal lattice. So maybe heating this up again or breaking it down, releasing the gas, and analyzing the amount of argon that comes out of it, knowing that the only way argon was in this mineral in the first place is because it used to be potassium, and if we know this half-life of potassium, that will inform us the relative age of the mineral. So this will extend back hundreds of thousands to hundreds of millions of years. Hundreds of millions of years now is kind of getting us into the more geologic scale, or determining the age of volcanic rock, igneous rock, which are the relatively young ones from a geology perspective anyway. After this, getting further back now, we have uranium lead dating. This is our last one. This one's also introduced in the mineral structure. We have multiple isotopes here of uranium-238 and uranium-235 decaying into lead as like the resulting or the daughter element, if you will. These half-lives are 704 million years, and for uranium-235, uranium-238 is 4.5 billion year half-life, which is almost the age of Earth itself. So the deal with these ones are they're included in the mineral structure again, but it's known as or specific minerals with a high closure temperature, meaning they're really unlikely to have their geologic clock reset, if you will, by successive heat or pressure or metamorphic events. So when the Earth itself was starting to form was the time we had the highest intensity of heat, highest intensity of pressure to kind of form these high closure temperature minerals containing uranium of these very isotopes that can gradually decay into lead. And there's a lot of elements in between and potentially after, but lead 206 and 207 are the isotopes that are most often analyzed for this uranium dating. And what else do we have here? You'd only use this on the extremely, extremely old sediments or rocks, usually the oldest rocks on Earth, because this is millions to billions of years as the effective range here. Other uses of oldest rocks on Earth, the reason we know or we predict that the Earth itself is 4.6 billion years since formation are the really old rocks of like the Canadian Shield somewhere in Australia too, I think, are another exposure of these, but oldest rocks in the world. The reason we can put an age on them in the first place is because of this uranium isotope sequence. Lead is not only relevant in this really old sequence. We have a lead-210 to lead-206 isotope that's used for more recent sediments of only a 20-year half-life. So my personal experience with this is from undergrad as well. We did a research project about taking sediment cores from the bottom of lakes to analyze how is the deposition of sediment changing over time. as the watershed of this lake was kind of natural, forested, undisturbed, eventually converted to agriculture with the settlement of the land, and then restored back into perennial vegetation, for example. How do we figure out the age of any of these sediments anywhere in the profile? We used lead-210 as the isotope for that example. So those are all the different strategies or ways that we have absolute dating. To shift it back into our more relative dates, or back into the applied hands-on. Let's start looking at some soil profiles now. The relative dating examples in the form of a chrono sequence. So, lucky me, we get to talk about glaciers once again, since I really love glaciers. This specific glacier is up in Alaska. This is the Mendenhall Glacier. Anybody's been to Alaska or familiar with it at all? This is a popular one. And we have a chrono sequence here of 5 glaciated soils of different age. So what remains of the glacier is up here on this kind of map view of this city area. And we know this glacier is gradually retreating. So by retreat, we don't mean it's flowing backwards necessarily. The glacier is still always flowing downhill. It's just melting at a rate that outpaces the glacial advance. So we have a chrono sequence set up, or soil scientists have done this in a classic study. We have 5 different sites in this Mendenhall Valley. Where site 1, right kind of in front of the glacier, has been only approximately 10 years since that spot itself was under the glacier. And then all extending through years. So site 2 is 38 years old, up to 70, 90, and then 240 years post-glacial retreat. The reason we know these years, well, humans have probably been there for most of these and can kind of measure the progress directly. But if we can't do that, things like tree rings, things like our ecological succession, if we know based on the plant communities that are growing there, the stages that this glacial landscape progresses through, we have a good idea of the relative age and the relative melt rate of this glacier. So again, it's kind of contained in all the same environment here. We've got the same parent material, glacial till probably, the same climate experiencing. Vegetation is going to change over time naturally, so that's important to still recognize. That's not completely isolated, but this is one of the best ways we can compare different aging rates or how soils are developing through time. So at our first site with the soil pit, at least with site number 2 at 38 years old, we have 2 horizons here, maybe 3. A thin OI at the surface with some kind of litter accumulating in the last 30 or 40 years. And then we have an A horizon to about 18 centimeters. Kind of hard to tell a change. I see a tiny little different coloration here, right where this first marker is, just above 20. That's probably a really lightly developed little baby A horizon. And our vegetation here was alder and cottonwood as kind of an early successor, early colonizer for just a new landscape in general. So that's where we're starting. Moving on to the next 2 sites under 70 and 90 years of soil formation. We still have an OI at the surface, probably a little bit thicker with more organic material accumulation. But now the A horizon is gone. It's been all leached out. We have an E horizon directly under the surface over a BS horizon, right? And no A horizon. So where we maybe had melanization starting as a soil process in the first one to get that little bit of A horizon going, something changed in the processes that podsilization is now dominant. We're leaching out all of these materials from the E horizon, keeping them in a BS, and then we lost that A horizon. So vegetation was spruce and hemlock here, probably good for acidic conditions. And then as development continues up to 240 years ago, we have this OE horizon, which is one of the older forms of O horizon, more progressed decomposition of organic material, and then an E horizon over BHS. Now we form this H, which is like the humic materials, humic substances, that really orangey color underneath the E horizon under a mature spruce and hemlock stand. So this profile forming under only 240 years, kind of as a measured chrono sequence. So the takeaways from this, at least, are that the A horizon had formed by 38 years, but then it was gone within the next 30 to get to 70 years. representing some kind of change in the soil processes. And then also by the time we reached that 240-year age, we had changed soil orders. So what started out as an endosol, a cryo-cement, we'll talk about classification a lot coming up in this class, but it only took us about 240 years to finally reach a spodosol with that BHS horizon, enough accumulation there. And that's kind of just the representative or the representation of that graphically. A more local example of one of these chronosequences, which we can consider, is just down in the Boise area. Boise set up on a lot of like these benches or terraces, which are themselves stream and river terraces. We can put an age on them thanks to the combination of 14C dating and potassium argon dating on these different levels of river terrace. And these kind of main ones here, the Boise bench itself, kind of where downtown is really only less than 15,000 years old. And then as we gain elevation, as we go up these kind of layers of the landscape, Sunrise Terrace of 130,000 years. Up by the airport, Gowanfield is 300,000 years. And then now up to 10 Mile at the very top, up to 1.7 million years old of just carving through erosion, I suppose. And then if we dig a soil pit on each one here on the Boise level, Boise bench, we've got a soil profile with this BW and BK kind of starting to have B horizon development going on, a lot of calcium carbonate accumulation over a C horizon. And what we're experiencing is the development of a durapan, a BKQN alphabet soup horizon here, where so we don't see it at all in the first soil pit. With 130,000 years of aging, we start to have this kind of baby development. Duranodes are specifically the process that this represents, where we start to have kind of cementing going on in some little parts of the profile. But then by the time we get up to maybe airport level, 300,000 years, we now have a pretty pronounced durapan formation, this kind of cemented layer, really hard, root restrictive for sure, after 300,000 years. But then as the years progress, millions and million, or over a million pass, we have this extremely prominent durapan, maybe another change in the soil processes where instead of adding material, we're now eroding it away. Maybe the soil profile is being carved out by wind and water erosion above and below this durapan itself, which really restricts not only plant growth, it's also going to withstand erosion really well. Really prominent durapan there. So just to wrap up, we can put this into a chrono function. So we know the ages and we know these specific soil properties such as calcium carbonate on the left here through this BK horizon, and then also the silica accumulation, which is the Q subordinate distinction within the BKQM. We can apply this function, get a prediction on it. So we could go out maybe in a similar area, characterize the amount of calcium carbonates, and obtain an approximate age based on this kind of age model or chrono function. Just to wrap up then, tephrochronology, we can also apply this in the Northwest with volcanic ash sediments. So dating of any volcanic ash eruption, knowing that they'll have their own inherently different chemistry with some kind of different magma source or different environment of eruption. Gives us different mineralogy or different chemistry that we can track. And then it's also possible to get absolute dating on these through our isotope methods. Good for correlating and comparing across landscapes because we know that the volcanic ash was probably deposited exactly at the same time all across the landscape. So this is a really multiple paramaterials, right? We get the 5AB horizon. It's all buried, multiple different events of ash, all stacking up on top of each other. We call that tephrochronology for volcanic ash. And then lastly, the parting thoughts here are a general timeline of soil development of each of these formations. The saying that people like to throw around is 1 inch in 100 years to develop new soil. I think the more accurate or more closely predicted global average is around, for 1 centimeter of soil, 178 years. Different areas are going to form faster than others, but the main takeaway is that soil formation happens really slowly. We should consider it a non-renewable resource, really important for not only our current lives that we live with, supporting agriculture, supporting our whole society, also combating climate change. So we're more in the business of eroding soil rather than forming new soil. As humans, that we can't really wait for new soil to develop as much as we might like to. So that'll do it for today. Stop the share. We got lab coming up. Another field trip today. I'll see you guys at 1:30 in the lab room. And then review on Tuesday for our test on Thursday. Thanks, everyone.